I came across a video the other day by a channel called Dialect. The name of the video is Logic at its Limit, the Grelling-Nelson Paradox. I'll put a link in the description box. The majority of the video was spent explaining the paradox itself, and at the end, the paradox was said to be equivalent to Russell's paradox, and virtually equivalent to Godel's incompleteness theorem, as well as Turing's halting problem, though I'm paraphrasing. No solution to the Grelling-Nelson paradox was offered, and the narrator stated that if a solution were found, it would strike a crack in an edifice which has dominated mathematical and philosophical thinking for well over a century. So that's what I'm going to try to do today. First, I'll briefly lay out what the Grelling-Nelson paradox is. It turns out that there's a word used to describe words that describe themselves, and that word is autological. For example, the word unhyphenated is unhyphenated, so that makes it autological. There's also a word used to describe words that do not describe themselves, and that word is heterological. So the word hyphenated would be heterological because it's not hyphenated. Now here comes the paradox. Is the word heterological itself heterological or autological? Logically, every word must be one and only one of these two. No word can be both, and no word can be neither. That's the law of non-contradiction. As Dialect similarly noted, most people would probably shrug this off as simply an inconsequential play of words. And as I intend to show, it is an inconsequential play of words, but not simply so. The problem deserves more attention and respect than that. And if you don't see that, then you don't genuinely understand the problem. And the problem is that this inconsequential play of words has the appearance of really truly violating the law of non-contradiction, which would make it a real-life contradiction, not just a hypothetical or fictional one. The solution to this paradox is the same as the solution to another, simpler, and more familiar paradox, the liar paradox, which can be seen in the sentence, "This sentence is false." Like the Grelling-Nelson paradox, this paradox should be respected, as they are so similar they had the same solution. And the solution is to realize that we have defined something to be inherently self-contradictory at the start. Consider the following definition. X is a statement that is not X. If you try to draw conclusions from this definition using logic without realizing your initial error, it's going to seem as if logic has been broken. It's not always obvious what has been defined in an inherently self-contradictory way, and it may not always be just a single word that is the root of the problem. Consider the following two sentences. The sentence below is true. The sentence above is false. The problem here does not arise from any single word or even a single sentence. The problem arises from the combination of the two sentences. Furthermore, the problem is not inherent to the sentences or words themselves, but rather our interpretations of them. So the paradox arises not from the symbols used to express it, but from the combined meanings we give them. It's also worth noting that truth is not always absolute, objective, or unconditional. Consider, for example, the statement, "Earth is 1,000,000 miles away." The statement may be true for some things, and perhaps one day for some people, but it's certainly not true for everything or everyone. So it's true in one sense, and simultaneously not true in another sense. Its truth value depends on whom or what Earth is being said is 1,000,000 miles away from. So when we ask whether something is true or not, and fail to arrive at a satisfactory answer, but not from a lack of information, it might help to remember that truth is conditional on the meaning we give something, and is neither an inherent nor real property of anything real. As for the Grelling-Nelson Paradox, the word heterological has been defined in a way that is inherently self-contradictory. And this may be an unavoidable problem with language in general. The power of language is the power to reference things with symbols, which includes the power to self-reference and self-negate. The point is, those of us who have been greatly troubled by these and similar paradoxes shouldn't let these things trouble them anymore. The Grelling-Nelson Paradox and liar paradox are, in fact, contradictions, but only because they've been indirectly defined that way. So they're not contradictions in any consequential sense. I can see why Dialect thinks the Grelling-Nelson Paradox is equivalent to Russell's paradox, which defines a particular set to contain all sets that do not contain themselves. The language sounds very similar, and autological and heterological words do form separate sets. But the Grelling-Nelson Paradox is about words, not sets, while Russell's paradox is about sets, not words. So the solutions are different. The solution to Russell's paradox is far simpler. The set that Russell defines does not exist. The paradox is often stated in a more accessible way, called the barber paradox, which goes something as follows. In a certain town there lives a barber who shaves only and all men in that town who don't shave themselves. Does the barber shave himself? The solution is, there is no such barber. My understanding of Godel's incompleteness theorems come from three sources. One is a Veritasium video, which I highly recommend for anyone wanting an introduction to this subject, as well as anyone who simply enjoys a good Veritasium video. Another was a video by, and I'm not sure I'm pronouncing this correctly, Mosen Kani. As you might concede, the written part of his presentation is formal. But as he talks about what he's writing, he does try to explain it in a way that's accessible to a more general audience, but one with at least some skills in math and logic. He talks about both theorems, but it's his explanation of the second theorem for which I find his video so valuable. His explanation of the second theorem was by far the best on YouTube that I could find. My third source for understanding Godel's theorems was the Wikipedia article, Godel's Incompleteness Theorems. I didn't read it all, and I certainly didn't understand it all, but it did help to fill in some gaps of understanding left by the videos. So Godel came up with two incompleteness theorems, and both revolve around a version of the liar paradox. The first theorem basically says that within any given system of math, there are statements that are true, but can't be proven true by the system of math that the statements are expressed in. Godel proves the theorem by creating a statement similar to the liar paradox, in the language of a mathematical system, and then using logic, proved the statement had to be true. The statement basically translates as, there is no proof of this statement within the system of math that this statement is written in. Now, analyzing this statement using simple logic rather than the math system that the statement is written in, the statement cannot be false, as that would mean there is proof of the statement within the system of math that the statement is written in. But if there's any kind of proof of the statement, then the statement is true. So by using simple logic rather than the math system that the statement is written in, we have just proven the statement can't be false and is therefore true. And that's how Godel proved that for any particular system of math, there are true statements in that system that cannot be proven by that system. My objection to this theorem is that the statement doesn't seem to be genuinely mathematical in nature. It might technically be expressed in a system that includes mathematical expressions, but the statement itself doesn't seem mathematical. It doesn't seem to express any arithmetic or relationships between numerical variables. So the point that Godel proves feels hollow. I don't feel that he's actually proven that within any system of math, there are genuine mathematical statements that are true but can't be proven within the systems they're expressed in. Instead, I feel that if we were to just revise our math systems so as to stop allowing non-mathematical statements to be treated as if they were mathematical, then perhaps a complete and consistent math system could be achieved. So based on Mose and Connie's explanation of Godel's second theorem and the Wikipedia article mentioned earlier, I've translated the argument into a form that I hope is even more accessible. And that form is as shown. I'll give you a few seconds to pause and take it in. My first objection to this argument is that it seems to equivocate on the word consistent. The word consistent, as it is used in this topic, is usually meant to describe a system that doesn't produce any proofs that contradict each other. But the term can also be used to describe a single proof that doesn't contradict itself. So there are really two kinds of consistencies to be recognized here: consistency within proofs and consistency between proofs. Godel's argument is mainly understood as proving that consistency between proofs of a system cannot be proven by that system. However, statement 2 is mainly understood to be talking about consistency within proofs, and that makes a difference. In the first place, this is special pleading. Proofs in general don't normally include a proof of consistency of any kind, and consistency within proofs, in particular, is just assumed as an axiom. If it weren't, then we wouldn't be able to prove anything by contradiction, which is exactly what Godel's argument aims to do. Second, if statement 2 is talking about consistency within proofs, then the conclusion is M cannot prove M is consistent within proofs, which is not what was intended. If, however, we interpret statement 2 to be talking about consistency between proofs, then the statement is false. Whether or not M can prove X has nothing to do with whether or not M has proofs that disagree with each other. It's conceivable that M is inconsistent within at least one proof and has a proof of X, yet has no proof that disagrees with another proof. One possible example of such a system might be the system of logic, formal or otherwise. Consider yet another version of the liar paradox, one that resembles Godel's argument. Go ahead and pause if you need to. The source of inconsistency isn't really so much in the system of proof, but rather it is in the definition of X, as I explained in the first part of this video. If there's any fault with the system, it would be that it permitted the definition. In any case, I don't think it indicates anything seriously wrong with logic. But getting back to Godel's argument, this example shows the possibility of a system that has proofs which contradict themselves, but has no proof that contradicts another proof. Since we would be inclined to assume that logic is still consistent between proofs, even if it's not consistent within this one proof, and even appears to actually prove X. So just because a system is consistent between proofs does not mean either that it's consistent within proofs or that it cannot prove X. So if we interpret statement 2 one way, the statement is false, rendering the argument unsound. And if we interpret the statement another way, the argument ends up concluding something other than what was intended, based on special pleading. Now, I don't actually think any system can prove its own consistency, of any kind, for the simple reason that to do so would be circular reasoning. Imagine there's an algorithm that can predict, within a finite and reasonable amount of time, the number of steps any algorithm whatsoever, without exception, takes before it stops, or halts. Also imagine there's an algorithm that will only halt if the first algorithm predicts it will never halt, and will never halt only if the first algorithm predicts it will halt. Obviously, what the second algorithm will or will not do cannot, in principle, be predicted. The official response to the halting problem is that no such algorithm that can predict whether algorithms halt or not exists. But this seems like a hasty generalization. The halting problem really only proves that one kind of algorithm in particular can't be predicted. And that's just because that particular kind of algorithm is unpredictable in principle. It doesn't prove every algorithm is unpredictable in principle, or that there can't be algorithms that can at least predict what some algorithms will do. Thank you for watching. If you like this video, please remember to give it a thumbs up.